Okay.
Whole chapter 1, the metallogenesis part, and the genetic terms of table 1.1 provide the basic vocabulary of metallogeny. Let's go to table 1.1. Yeah, same genetic denotes ores and minerals that same genetic denotes ores and minerals that formed at the same time as the host rock, most often applied to sedimentary rocks and ore. Epigenetic ores were emplaced into pre-existing rocks of any origin. Example veins, metasomatic ore. Hypogene ores that were formed by ascending solutions. Example Mississippi Valley type lead, zinc. Supergene ore formation by descending solutions, meteoric water interacting with rocks during superficial weathering processes. Lateral secretion, concentration of metals by abstracting from surrounding rock. Endogenetic concentration caused by processes in the Earth's interior, magnetism or metamorphism. Exogenetic concentration caused by processes at the Earth's surface, sedimentation and weathering. Okay. The genetic terms of Table 1.1 provide the basic vocabulary of metallurgy. The non-genetic descriptors stratiform, layer-shaped, and strata-bound, restricted to certain strata, only denote shape and position of an ore body in relation to sedimentary features, not its origin. Comprehensive explanations of geological and mining terms can be found in the Dictionary of Mining, AGI 1999, and the Glossary of Geology by Neuendorf et al. 2005. Geological time nomenclature in this book follows Walker and Wiesmann 2009. Magmatic ore formation systems, a very large and diverse group of ore deposits, originates by various processes during formation, evolution, emplacement and crystallization of silicate melts, magmas in the upper mantle and in the Earth's crust. Most post-Archean magmatic rocks can be classed according to their plate tectonic environment. Okay, so most Post-Archean magmatic rocks can be classed according to their plate tectonic environment. Rocks of the Ophiolite Association basalt gabbro ultramafic rocks are remnants of former mid-oceanic ridges, back-arc basins, and of early and primitive parts of immature oceanic island arcs. Mature island arcs and active continental margins are distinguished by profuse amounts of orogenic andesites and equivalent intrusive magmatic rocks. Continental collision causes melting of oceanic crust and voluminous granitic magmatism. Continental rifts are associated with bimodal alkaline volcanism, basalt and rhyolite. Extensional deformation of continents and mantle melting result in emplacement of layered mafic intrusions, flood basalts and alkaline magmatic provinces. Okay, so extensional deformation अगर हुआ then we will have a deformation of continents and mountain melting, resulting in emplacement of layered mafic intrusions, flood basalts, and alkaline magmatic provinces. Most notable are subvolcanic ring complexes and kimberlite dikes. Subvolcanic ring complexes and kimberlite diatreme that transport diamond from 200-kilometer depths to the surface. The association of certain igneous rocks with specific metal ores was established long ago. Ultramafic rocks host ores of nickel, chromium, and platinum, gabbro and norite, copper, cobalt, nickel, iron, titanium, and vanadium. Andesite and intermediate intrusive rocks induce copper and gold ore. And granites are related to beryllium, lithium, tin, and tungsten concentrations. Essentially, this distribution was understood as a result of the geochemical fate of the different metals during fractional crystallization, solid liquid fractionation of silicate melt bodies. Goldsmith, 1958. Meanwhile, magmatic rocks can be further differentiated according to plate tectonic setting. Source rocks, degree of partial melting, role of volatiles, and many other genetic variables. Examples of various basalt types, N and E morph intraplate island arc. Okay, we shall see later in this chapter that some of these rock classes are related to specific ore deposits. Impact magmas result from heat and high pressure caused by collision of extraterrestrial bodies with the Earth. Melting affects part of the crust and in rare cases even the upper mantle. Impact magmas differ chemically from other melts because whole volume of crust are liquefied, whereas normally partial melting is the rule. In addition, the impacting body may induce geochemical anomalies, especially regarding siderophile elements. Uh, Platinum, iridium, cobalt, and nickel. Post-impact cooling can induce hydrothermal systems that are able to redistribute matter and provoke ore deposit formation. In conclusion, the geodynamic environment controls the formation of ores from silicate melts in several ways. At the scale of ore forming processes caused by single magmatic bodies, the following major genetic processes stages are differentiated. Orthomagmatic ore deposits are formed before the melt cools to complete solidification, or in other terms, in the liquid stage before solidus. Pegmatitic ore deposits are the result of segregation of small residual melt patches from a large crystallizing magma body approaching the solid state. Fertile pegmatite melt is characterized by high counts of volatiles and of incompatible and rare elements. Magmatic hydrothermal ore deposits are produced by super or subcritical fluids, solutions, and gases that are segregated by all magmas which had more dissolved volatiles, H2O, CO2, sulfur, boron, fluorine, chlorine, etc., than the amount that could be accommodated in silicates during crystallization. Because of this connection, the time of fluid phase expulsion is commonly coeval with the formation of solid phases minerals from the melt. A significant part of the geochemical signature of magmatic hydrothermal ore deposits is determined by processes at the magmatic stage. Now, orthomagmatic ore formation oxide, magnetite, ilmenite, chromite, base metal sulfide, nickel, copper, and ore of precious metals, platinum, palladium, gold is often found in ultramafic and mafic igneous rocks. More rarely, magnetite occurs in intermediate and felsic silicate melts. Texture and many other observations show that these ores were formed at magmatic temperatures, while the melt was essentially liquid and before total solidification. Therefore, this class of ore deposit is called orthomagmatic. Okay, so more magnetite. What happened here? Eh, More rarely, magnetite occurs in intermediate and felsic rocks. Textural and many other observations show that these ores were formed at magmatic temperatures while melt was essentially liquid and before total solidification. Therefore, this class of ore deposits is called orthomagmatic. Numerous observations suggest that enrichment processes concentrate segregate low metal traces from a large mass of silicate melt into small volumes. A common evolution is that the parent melt evolves towards saturation so that either a solid, example chromite, or a liquid, example sulfide melt, accumulates the metal in question. At some stage, residual fluids may intervene. Many parameters influence these processes, including the depth of intrusion, tectonic activities, the temperature gradient in space and time, fractional crystallization, dynamics of the melt body, example convective flow, repeated injection of fresh melt, assimilation of country rocks, sulfur or external fluids, liquid immiscibility of ore and silicate melts, and mixing or resolution. Because of their higher density compared to silicate liquids or melt droplets or solid ore phases typically accumulate above or within floor rocks, which may be cumulates below still liquid lava magma. gravitational accumulation. Consolidation of cumulate minerals can lead to expulsion of intercumulus liquid filter pressing. The consolidation of cumulate minerals can lead to expulsion of intercumulus liquid filter pressing. As the system cools or melts themselves may then separate into cumulus. Okay, iron sulfides and residual liquids are key copper-rich sulfide model. Various mathematical models have been proposed that describe the orthomagnetic enrichment process. Concentration of metals such as PGM, platinum group metals, gold, nickel, and copper in sulfide melt is controlled by the Nernst partition coefficient. Concentration of metals such as PGM, platinum group of metals, gold, nickel, copper in sulfide melt is controlled by Nernst partition coefficient T between sulfide and silicate melts and by kinetic factors. This equilibrium is exposed by calculating the silicate by sulfide liquid mass ratio, the R factor. Okay, the R factor. A zone refining model is appropriate when, for example, sulfide droplets sink through a magma chamber and collect chalcophyte metals. Limited base metal content but very high PGM enrichment can be explained by resorption of iron sulfide liquid in undersaturated magma. Okay, so limited base metal content but very high PGM enrichment can be explained by resorption of iron sulfide liquid in undersaturated magma. In this process, we will keep it to this much and continue the next part.